Hello, and welcome to my talk about token swapping. I am Tillman Milzo, or just Till, and this is joint work with Günther Rothe, Antonis Thomas Lajonaris, Yoshio Okamoto, and Takayaki Uno, and we are from all over the world. Berlin, Hungary, Switzerland, and Japan. Okay, so these are my co-authors again. This is Günther Rothe, Lajonaris, Antonis Thomas, Takayaki Uno, and Yoshio Okamoto. Okay, so let me tell you about token swapping. In token swapping, you've given a start configuration, which looks like this. This is a graph, and on each vertex of the graph, there's a token, and then you're allowed to swap these tokens along this graph, and a swap is just the exchange of two tokens on adjacent vertices. Bam. And another time. Bam. And at last. And now we reach the final configuration where each token is at the correct vertex. You're indicated by the same color. And we use three swaps. And in general, we ask for a given graph and a given token configuration are k-swaps enough. That's the algorithmic questions we are concerned in this talk. So what did people do so far? Not so much, actually. So there's a two approximation for trees. There is for all kind of graphs which can be described by one or two numbers, it has been solved. And this is often in the context of sorting rather than in the context of token swapping, though these people didn't know about token swapping. And there are some variants for which hardness has been shown, NP hardness. Yes. So when we submitted this work, I talked about it with Edouard Bonnet and Pavel Jajewski here in Hungary, and we could come up with a bunch of new stuff, simpler hardness proofs, parametrized hardness, some parametrized algorithms, and more refined lower bounds for more restricted graph classes. This is very interesting, and we just uploaded it to arXiv, so check it out. But today I want to talk about the results that we attained earlier with this other group of authors. And so we have another two approximation on trees, which I will explain you. And actually it's also four approximation on general graphs, and there's two approximation algorithms different. And yeah, it's nice to see that it also works for general graphs. And we can complement this nicely because we can also show APX hardness. So we can show while we have a constant factor approximation, you cannot do better than constant factor approximation. But of course, we don't know what is the right constant. We can also show that there's no 2 to the little o of an algorithm under the exponential time hypothesis, and the trivial algorithm runs in 2 to the o of n log n time by just traversing the space of all possible configurations from the start configuration. And we of course have also NP hardness. So basically all these results here are just one reduction which we carefully squeezed. So we made sure the reduction is gap preserving and also linear. So we have to cut out everything that's unnecessary to get these results from this one reduction. Okay, before I tell you what we did and how we did it, why did we do it? I guess there are four motivations to work on the token swapping problem. The first one is a very natural formulation. The problem is immediately clear. It's understandable for non-scientists. You can explain it basically everyone on the street. Yeah, this is nice. The second reason is it's fun. It really is. You have your you have your magnets and you have your whiteboard and you have your configuration. You try to figure out which is a shortest sequence of swaps, and this is fun. Yeah, you could imagine this being the new game on your smartphone. If that would be available, I would play it. I don't have a smartphone, but still I would play it. but I haven't found something like this. So if you're a game designer, go ahead. Maybe more serious, but not more important motivation is that it fits into this framework of reconfiguration problems. The classic reconfiguration problem is motivated by motion planning. In motion planning, we have a robot, and that robot goes from one configuration to another. Maybe it wants to move a book from some place to another place on the shelf, and it doesn't want to collide with other robots. So this would be a reconfiguration problem. And a lot of those are studied. We don't see a direct connection here to motion planning. Yeah, but it definitely fits into this framework. And the last motivation is this close relationship to sorting, which I want to explain you briefly. So let's say we have a path. Let's say this one. Then this token. So okay, then we have, first of all, we have a permutation here between the tokens. We have always a permutation between the tokens and the vertices, but in the path it's most obvious. And then this token wants to go most to the right, and this token, the dark blue one, he wants to go not as much to the right. So it's reasonable to swap these two tokens, and this is exactly, and so we have to swap these two tokens at some point. And so we can swap them straight away. So it is exactly a bubble sort step, every optimal step in the token swapping problem. And let's say you want to ask, okay, I want to have an optimal sequence of sorting steps, and I can do any, not just adjacent ones. Then this would correspond to a click, and it was studied before in a click. And then the optimal solution is n minus the number of cycles of the underlying permutation. Similar studies has been done when you say, okay, I always want to swap with the first element of my sequence, then that would correspond to a star. And now we go away from that permutation, but you could think of this permutation being there somewhere underlying, and you want to sort this permutation. And really the solution also has properties of your permutation. Okay, so this would be why we study it. Okay, so now let us go to let me try to explain you the approximation algorithm. And it's based on trying to reduce in each step the distance of each token to its target vertex. So with, let's say, Li denotes this distance, then it's clear that the optimal solution needs at least all these distances divided by 2. And the reason is because each swap, 2 tokens are involved, and each of them reduce its distance by at most 1. Maybe it doesn't reduce its distance, or it might even increase its distance, even in an optimal solution. But yeah, it cannot decrease the distance in a single swap by more than 2. Okay, so we will use this to show that our approximation algorithm is into approximation algorithm for trees. Okay, so we first introduce this directed graph. So for each token, we just draw an edge, the directed edge to where it would decrease its distance. So this token want to go there, so that would be the direction of decrease. So this brown token, it wants to go there, it wants to go here, so that would be the direction of decrease. And then using this graph, we can define different kind of swaps. The first one would be the most natural one. It's called a happy swap. Happy swap means that both involved tokens decrease its distance. This is what we want. But obviously, we cannot guarantee that this always happens. So we also have to deal with different kind of swaps. And those kind of swaps we choose is the unhappy swap, which is a following swap. So one token's already at the right spot, and the other token tries to go there So we have to move that token with its right spot out of the way. So you can see here an example. This brown token wants to go there. So it has to pass by this blue token with already right spot. So it's clear that this kind of swap is unavoidable. But we call it unhappy because this blue token, it was already where it wanted to go and has to move away. There are also different kind of swaps we could consider, but we don't care about them. And what I first want to show you, there's always a happy or unhappy swap. That's very simple to see. The proof is follow any directed path. So let's do this. Start anywhere and then follow this directed path. And because we're on a tree, at some point we end up in a loop, either a loop on an edge or a self loop. And in either case, we're having either a happy or unhappy swap. So we are always in a situation that we have either unhappy swap or unhappy swap, or all the tokens are resolved. Okay, the next lemma is that there can't be too many unhappy swaps, because on one edge, after I perform the unhappy swap, I cannot perform an unhappy swap again. Why is this? So let's say here this green token wants to go in that direction, and the orange token is already where it is. And we perform this unhappy swap. Then this orange token is not in the right place, and it wants to go in this direction. So because we only perform happy and unhappy swaps, it will not go in the other direction. And on this other token, on this other vertex, there will not be a self loop, because the only way there could be a self loop would be if there would be the orange token, but well, the orange token isn't there yet. And it won't come there before we have performed, well, a happy swap, because an unhappy swap can't happen here. So yeah, so we do a lot of swaps, the orange token won't swap, and when the orange token will swap, well, there will be a happy swap. Yes, so now we can end this consideration of the approximation algorithm. All we have to do is some calculations. So we want to bound the total number of swaps by the optimum. So first we bound by the happy and unhappy swaps. And as we just saw, the number of unhappy swaps can be bounded by the number of happy swaps, so we have twice the number of happy swaps. So as each happy swaps decrease the distance by 2, this term is upper bounded by the total number of distances. And this is upper bounded by twice the optimum, which I showed on the first slide about the approximation algorithm. So we see this algorithm is indeed a 2 approximation. The nice thing about this is that it's also a 4 approximation for general graphs. Why? So we can define the same kind of graph, this directed graph, for general graphs, not just for trees. So here maybe the token which is here might want to go there. So it goes either here or it goes there. That would both decrease the distance to its target vertex. But nevertheless, we can find those directed cycles, which we then call happy cycles accordingly, or we find unhappy swap. So either of these two we will always find. Now these happy cycle swaps we can resolve, because if we have one of those, we just move this token which is here along the cycle in the wrong direction, and then everyone gets resolved, right? If I move this token here, then this token goes in the direction that it wants. That would resolve the cycle. We need L-1 swaps to do this, and the total distance is reduced by L for a cycle of length L. So this is not as efficient. The smaller the cycle, the more efficient it is, but the same proof goes through, and then we have a 4 instead of a 2 approximation. Okay, now I want to talk about lower bounds, which I already told you about, and now I want to show you how they work. So I started maybe with an overview. So this lower bound is technically very demanding, and it has a lot of nice ideas. So first of all, the overview is that we do 3 reductions. First, we go from tree-thread to some special disjoint path problem, which I will define. Then we go to some variation of token swapping called colored token swapping. And then with some nice trick, we show you how to go from token swapping, from colored token swapping to token swapping. The reason why this reduction gives us all the nice lower bounds we want to have is because it's linear and gap preserving. So we must be careful at each step that we don't introduce unnecessary stuff. So I will present it to you. There is some unnecessary stuff, but we have some ways to get rid of it. I will not mention these things later again. Okay, so what is a special disjoint path problem? We've given a graph which can be decomposed into layers, and all the edges are just between adjacent layers, so either between v1, v2, or v3 and v2, or v3 and v4, and so on and so forth. And then we want to find path from the first layer to the last layer, such that all the vertices are covered here, and all the paths are vertex disjoint, and also that we specify for each path where it starts and where it ends with this function phi, or this bijection phi. And then the question is, can we find these paths as specified? This is a special disjoint path problem. The color token swapping problem, which I mentioned also already, is a generalization of the token swapping problem with just colors can reappear more often. So here color orange appears 3 times, so there are 3 vertices with color orange and 3 tokens with color orange, and an orange token, surprise surprise, has to end up on an orange vertex. Not necessarily the one it starts on. So maybe this token wants to go here, and this token wants to go there, and this token wants to go there. Who knows? So this is generalization of the token swapping problem, because if each color would be unique, then this would be the token swapping problem as I explained it earlier. So let's start with the first step of the reduction from 3 satisfiability, so the special disjoint path problem. And here the idea is very simple. We just build some gadgets. For the variable assignment, we have this gadget that we say, okay, the path has to start here and end here, and there are 2 possibilities. The path goes this way or it goes that way. And this would assign either truth or false, and whatever other path is free will be occupied by a full path. For the clauses, we have some complicated clause gadget, and for the path to go through, there must be at least one of the clause gadgets which is satisfied. One of these x must go in the right thing, and then things are happening here. But I want to explain it. It's pretty straightforward, but please look at the paper if you want to see these details. Yeah, so that would be that. How this works, so it's kind of a standard exercise, I would say. Okay, so then we can go from the special disjoint path problem to this color token swapping. So we somehow had first this part, and then we could do the reduction I showed you before. And this is actually quite a nice idea, I think. So we have given our graph, and we just copy our graph, and we give colors in a certain scheme. Namely, every layer gets a unique color, except for the last, where every vertex gets a unique color. And then we give every token the color of the layer before. So all the brown tokens want to go here, and all the red tokens want to go here, and here all the orange tokens want to go 1 layer backwards. And all of those tokens here, they want to go to the last layer, and they will represent these paths. So let's see. So if we have disjoint paths here, then we can move those tokens along these disjoint paths, and while this token will go forward, every other token will go backward and will end up in the layer it wants to. And these tokens here, they don't care where they go, as long as they go 1 layer backwards and only 1 layer backwards. And if we do this with all the tokens, all the disjoint paths, then each token's on the correct spot. That's a very nice and simple idea, and it's immediately clear that this is if and only if. So now let's see when can we go from this color token swapping to the token swapping. And here we have a special gadget which we invented. We call it even permutation network. So the idea is that there are some tokens placed here, and these tokens want to go there. And there's also some tokens which are kind of fixed, which are in here, which want to go somewhere. But the idea is no matter how you place these tokens here, it always takes the same number of swaps to bring them to the bottom. Well, this is not entirely possible because depending on whether the initial placement here corresponds to an even or an odd permutation, the parity of the total number of swaps are already given. But if we can restrict ourselves to even permutations, then we can achieve this gadget which says no matter how this permutation looks like, we always need the same number of swaps. So the way that we use this even permutation network is we use our original graph with all these layers, and we had that here there were different ways to how we can resolve these tokens which want to go on this layer. And then we say, okay, now they have to go further, but we don't really care how they go further. Because in any case, it takes the same number of swaps. So we don't really care in which way they go to that target layer. Like, we don't care in which way these brown tokens are arranged here and these red tokens are arranged here, because what happens is, so we give them all a distinct color then, and no matter in which way we do this, because of this even permutation network, they all need the same to resolve here. Okay, so that's it. So these are these two ideas we had here. It got very technical to make things linear and tight, and this description here is also tedious, and also this even permutation network is tedious, but it's not too hard, and this is how the reduction goes. I want to finish the talk with an open question. So I showed you this approximation algorithm for trees, but we think it's not tight. So is there a better consonant approximation algorithm, or even maybe a 1 plus epsilon approximation algorithm? What is the approximation factor for that algorithm I showed you? We don't know. We don't think it's 2. It's probably better. What about general graphs? There should be better approximation algorithms. But one of the problems we care most about is what happens on a tree. Specifically, we could imagine this problem already being hard on a spider. Can you find an algorithm for a spider, or can you show it's hard for a spider? Yeah, this is completely open, and I think kind of a challenging problem. So, yeah. Okay, thank you for listening, and please report us on your progress or write comments if you have further questions. But for details, please read the paper. Thank you.